The typical course in multivariate calculus generally starts with a unit on vectors, lines, and planes, probably there to serve as an introduction to thinking and visualizing in 3 dimensions. Now, Maple's Student MultivariateCalculus Calculus package has some tools for working with lines and planes, and it accessed either by a set of 16 commands or syntax-free using the context panel. So in this webinar, we're going to take a look at these tools, but we'll illustrate them with a set of examples that you would typically find in a standard course or textbook. There are 2 constructors, one for constructing a line object and one for constructing a plane object. Here is some notation that you'll see in these tables. So look, if you have an equation of a line or an expression which when set equal to 0 gives you a line, that will determine a line in the plane. 2 points, whether in 2 space or 3 space, will determine a line. A point and a direction, 2 space, 3 space, will determine a line. 2 space, 3 space, parametric equations, or a vector of expressions, each component of which is linear in the parameter. 2 planes determine a line in space if they intersect. A point and a plane determine a line in space. The line so determined is orthogonal to the plane. In 2D or 3D, a line object can be modified using the line object constructor. Now, likewise, plane is determined by an equation linear in 3 variables, or an expression which when set equal to 0 would provide the equation of the plane. 3 points determine a plane. A point and a normal vector determine a plane. 2 points and some vector determine a plane. 2 directions, 2 vectors, and a point determine a plane. A line and a point not on the line determine a plane. 2 lines determine a plane in the following sense. If the lines are skew, the plane will contain the first line and be parallel to the second line. If the lines are parallel or intersect, the plane will contain both lines. Point and a plane determine a plane that contains the point A and is parallel to that plane. And the plane, if you want to modify it, you can apply the plane object command to the plane object. Okay, so the things that determine geometrically a line or a plane are the same here in the packages they are with a pencil and paper. So you want to see how you can interact with these objects. So here are the commands in the package. Get the dimension of the object to a 3, get the direction of a vector along a line, get an intersection of 2 objects, determine the normal on a plane, just draw a graph. Okay, it's the one item that is not in the context panel. You can get a point on a line or a point on a plane, get the equation of a line, get the equation of a plane. These are queries. Do these objects intersect? Does this object contain that object? What is the distance between these 2 objects? Are these 2 objects equal? Are these 2 things parallel? Are these lines skew? Are these objects orthogonal? What is the angle between these 2 objects? What is the projection of this object onto that object? So these are the commands that are available. if you are looking at the equation of a line, you can get the equation of a line as this equation. If you have form equals, if you put an S on there, it'll come back with set braces. If you ask for the form to be vectors, you'll get this unmultiplied out vector form. There's your parameter t, direction vector, fixed point. If you say parametric, you'll get parametric equations. If you say symmetric, you get the symmetric equations. If you say combined vector, then this product is simplified, and you have the fixed point here, parameter, and the direction components. The equation of a line in space does not have a simple representation, so you would get an error. You could get the line expressed in space with a pair of equations, vectorially unmultiplied out, parametrically, symmetrically, or vectorially multiplied out. When you're looking at a plane, you're going to either get an equation, or if you put an S on the word equation, you will get the equation back in set braces. When we work with lines and planes in the context panel, pretty much what you do is you put the objects or their names in place, and then you go to the context panel, and in the Student Multivariate Calculus package, you will get an appropriate option for an action. There's a few places where you need to do either an evaluate and display in line, or hit the enter key so that Maple can actually see the content of the name in order to understand what it needs to do. Now, by means of examples, we're going to explore the use of these tools that enable us to work with lines and planes and some vectors. And here's an example. First one. Equation of the line. Through this point containing this direction. So let's follow this hyperlink. We go to a page where the example is reconstructed, and we can use this page for solving the problem. I'm going to solve it in two different ways, a syntax-free solution, and then I'll show you how the commands behave. For the syntax-free solution, install the student package. Show you this once here, tools, load package, Student Multivariate Calculus. When that's installed, point, vector. Point, square brackets, list. Okay, these square brackets make a list. Point is 3, 2, 1. That's the point. The vector, the direction vector, 2 minus 3, 5. Angle brackets, which are really inequality symbols. So, having made that sequence, go here to the context panel, Student Multivariate Calculus, lines and planes, you're making a line. So when you do that, you will get a pop-up in which you set the coordinate names. X, Y, Z are defaults. Pick OK. You get this line object. This is the way Maple says it's created a line object. If you use the context panel on that line object, lines and planes, you now have a choice for what do you want to do with this line object. And you can see the different things you can do. When you select representation, you get this pop-up. Parameter name, T is the default. You can change that. And then the form that you want the line to be given in, I have chosen here combined vector. So you now get the representation. Here's your point, fixed point on the line, 3, 2, 1. T is the parameter, 2 minus 3, 5 is the direction vector. This same calculation done with commands would look like this. Load the student package, and here, since you're using commands, I loaded the package with the with command. The line command takes as argument point vector, and I've assigned it to the name L1. I apply the get representation command to L1 with the option form equals combined vector. We get the same thing that we got up here from the context panel. And here, if you say form equals parametric, parametric equations. If you say form equals symmetric, symmetric equations. If you say form equal vectors, you get parameter times direction vector plus fixed point. There is, of course, the traditional vector approach, which we can implement here in Maple as follows. We write the direction vector v, that's its name. Here is the vector component-wise. Put an equal sign between, use the context panel to assign name. That takes care of that colon equal business, makes the assignment. The point, the fixed point, 3, 2, 1, is given as a position vector, so you make a vector out of it. R is the generic position vector to the x, y, z. And if you write R equals P plus TV, you will get R equals P plus TV. For a second problem, we are looking for the equation of the line that passes through 2 points. Again, let's go over to the end of this hyperlink, and we have a place where we can solve this problem. Again, the solution will be in terms of both syntax-free computing, and we'll show you the commands. So for the syntax-free solution, we load the Student Multivariate Calculus package. We're dealing with 2 points. So here are the 2 points, 2 lists. Again, context panel, make the line object. On the line object, you ask for the representation. If you choose combined vector for the form of the line, then you get fixed point. And this direction vector is the difference. 5 take away 3, minus 1 take away 2, so you get a minus 3, and 4 take away 1. So the direction vector is the vector between these 2 points. Maple did that work for us. Solving this with the set of commands in the package would go like this. Again, with Student Multivariate Calculus, line command is applied to the 2 points. Get representation applied to the line object with the form that you want, and you get the same, you can see that here if I scroll up, the same answer that you had up here. And then if you say form equals parametric, you'll get parametric equations, symmetric equations, form equal vectors, then you get this, but not multiplied out. Then the traditional vector solution would run something like this. The 2 points P and Q use an equal sign, but use the context panel to assign name. Generic position vector, and write R equals 1 point plus T times the direction vector, which is obtained by subtraction, Q minus P. For a third example, we are given 2 lines. 1 line here, 1 line here. These are the expressions for the lines in terms of parametric equations. We ought to show that these lines don't intersect and are not parallel, making them skew lines. Now, skew lines have a common normal, and when you get the common normal, you can use that to calculate the distance between the two lines. So let's follow this hyperlink over to this page where we can work on this problem. And again, we have two solutions, syntax-free and command-based. So let's look at the syntax-free solution first. So again, we load the Student Multivariate Calculus package. Now, the lines are given parametrically, so make a list of those three equations and apply the make line operation from the context panel and give it the name. So we assign to the name. So here you would assign to a name and give it the name L1. And here you do the same thing with the second line. Parametric equations make the line. So then we ask about skewness. So we write the names of the two lines. And here's an instance where you do evaluate and display in line, which has a keyboard equivalent. In fact, it has two keyboard equivalents. I always use Control equal, but I think Alt Enter is an equivalent. So Maple echoes back these two symbols for the line constructs, the line objects, and then you query Student Multivariate Calculus, lines and planes, and you query Skew. And Maple says true. And you can do the same thing with querying for parallel. You saw that if you pick that up, lines and planes, parallel. So this is our parallel. Maple says no. And if you do the third one, intersect, Maple says false, they don't intersect, consistent with being skew lines. So now that we know that the lines are skewed so that there is a common normal, we can get that common normal by several techniques. Two lines make plane. You get a plane object. You query the plane object for its normal, and you get the normal. A second method would be the way you would do it with a pencil and paper. You take the cross product of the vector directions for the two lines. So let's see how you would do that. Line, display in line, so Maple echoes back its symbol for the line object. You query the line for its direction, and then you assign it a name, so I call it V1. And you do the same thing with the second line. So now you have the two direction vectors. The cross product of the two direction vectors will give you the common normal. The cross product symbol I get from my favorites palette. Here, let's show you it here. And the way you populate your favorites palette is you find something you use and you want to use repeatedly, common symbols, you right click on it and you get this option, add to favorites. That's how I populated my favorites palette. That's where I got the cross product symbol. Just hit the enter, do evaluate and display in line, which is Control equal, and you get that common normal. So that's the second way to get the common normal. The distance between the two lines can be obtained. Write the names of the two lines, and then evaluate and display in line. So Maple exhibits these line object symbols, and then you go here to multivariate calculus, lines and planes, distance. Maple comes back and says, here's the distance, 16 over square root of 11. And then here, approximate to, and I picked 10 digits, and you have an approximation to 10 digits. Now, the command version would go like this. Okay, again, bring in a package, define the first line, you apply the line command to the list of parametric equations, same thing for the second line. Then you use the queries Skew, parallel, intersects. Yes for skew, no for parallel, intersect. Common normal. Get the normal for the plane formed from these two skew lines. You get the normal. Or you get the direction from the first line. You take the cross product with the direction from the second line. Those are the two methods for getting the normal. Distance. It's a command. Distance between these two lines. Get 16 over the square root of 11. And the one thing that you can't do with the context panel, but you can do with commands, is get plot. So get plot apply to line 1, apply to line 2, apply to one plane, apply to the other plane. Now, how are the two planes drawn? Get a point on line 1, use the normal, form a plane. Get a point on line 2, get a normal, draw a plane. And put it all together, you have 4 different graphs, and you have skew line, one plane, the other plane. This skew line lies in this plane, this skew line lies in that plane. The traditional vector approach to these 3 questions would run something like this. And I would suggest that this picture should start any discussion of skew lines. One line, the other line, common normal, parallel planes. Now, to do this with a pencil and paper in the traditional vector style requires the following calculations. You need to solve 2 equations, x of t equals x of s, y of t equals y of s. So you're looking for the x, y coordinates of the point directly under the 2 lines. Use the context panel. Here, I'll show you. Solve, right? You just pick solve. Then, having obtained the values of s and t at point on, think of it on the ground, you're looking up, and these 2 smoke trails above you that appear to cross. So the point on the ground is given by s is this and t is that. You need to plug in t equals 2/3 in this in the expression for z. Okay, that's the expression for z, and you would use evaluate at a point. You do the same thing for the other line. Plug in the value for s. If these 2 numbers were the same, then the 2 lines would have the same height at that point, and they would cross. They would actually intersect, but they don't. One is higher than the other. You can show that the lines are not parallel by taking the 2 direction vectors. Here I've called one P and I have one called one Q. If the cross product is a zero vector, then they're collinear, which would make them parallel. But this turns out to be the common normal, which we've already computed, and that's what we'll see here in part B. Part B asks for that common normal, but it's just been calculated right here when we took the cross product of these two direction vectors. Part C, done traditionally, profits from this drawing. Line 1, line 2. Point A on line 1, point B on line 2. By subtraction, you get the vector V from A to B. This green line represents the common normal. You project this vector onto the common normal and get the length of that projection. That will give you the distance between the two parallel planes. To do that, a point A, a point B, but you can use the fixed points on the lines. V is the vector here, B minus A, by subtraction. And then the scalar projection, V dot n, because n is a normal vector, V dot n over the length of n. So n over the length of n is a unit vector, and V dot the unit vector gives you the length of the component along that unit vector, and you get 16 over root 11. In example 4, we have to find the distance from a given point to a given line. This is a point on the line. This is the direction of the line. So let's head over here to the end of that link. Here is the point. Here's the definition of the line in terms of a fixed point and a direction. So using the lines and planes tools, we have a syntax-free solution that starts with loading the multivariate calculus package, a point, and a vector. Okay, that point is A. 1 minus 1, 2. The vector is the direction vector of the line. Right click. I'm sorry, not right click. Context panel, Student Multivariate Calculus, lines and planes. Make the line. You get the line object and give it the name L using assign to a name. Then write the name of the line and the point whose distance to the line you want to compute. Back to the context panel, Student Multivariate Calculus, lines and planes, and you have the distance option. Take that, you get this expression, and then that can be floated by this approximate. I picked 10 digits, and you get the distance. Command-based solution would run this way. Load the package using with. Apply the line command to the point A and the vector V. Give it the name L, assignment operator. Then use the distance command. Apply it to the line and the point from which you want to make your measurement to the line. Give that the name D, assignment operator. And eval F, evaluate floating. Apply to D will float that number, and this compares favorably with what we had above. The traditional solutions to these kind of problems rely on projection, and it really helps to have a figure if you're going to talk about projection. So in this figure, we have the line that's drawn in black. The point A, the fixed point on the line, is this red dot This is the direction vector of the line. This point up here is the point P whose distance you want to measure. By subtraction, you form this black vector from A to P. Project this black vector onto the green vector. So you're projecting it down onto the line. The projection happens to point in the opposite direction, but that's no problem. And what you really want is the orthogonal complement to that projection. That's this red line. And the length of that red line is the distance that we're looking for. Now, there is a task template for this. What are the task templates? Tools, Tasks, Browse, Table of Contents. We want to look down here in Linear Algebra, Visualizations, Projection, Plot onto a one-dimensional subspace. Here is the task template. You can insert it by clicking one of these two buttons. Default content means you get this extra verbiage. Minimal content means you get enough to make the thing work. I've got the task template already embedded in the worksheet. You can see here's the path to it. We got to get some data. So A is the fixed point on the line, V is the direction vector of the line, and P is the position vector to the point whose distance of the line you want to measure. So use an equal sign, then do an assign name. You get these three pieces of data entered. This is the task template. P minus A is the black vector that we see here. We are projecting that onto the green vector V, and you'll notice green here, V, green in this field here. Project onto V and get the orthogonal component. And you can see here a nice picture. This gray thing is the line. There's your green vector V. The black vector that you want to project, you project downwards onto the green vector, and the orthogonal component is in red. You see the red over here. Now you gotta get the norm of this vector. So what you want to do is you want to copy as mathml, and then you want to paste it. So when you go to paste it, you get this pop-up. It asks if you want the mathml to be converted into Maple's 2D math, and you say yes. So then you get this vector, and you've seen how to get the Euclidean norm. Vector here, go down to norm, take Euclidean, you get this number. You can approximate it to as many digits as provided. I picked 10. A vector solution from first principles implements these same calculations. The black vector, P minus A, you want the orthogonal complement. So this is the projection onto the green vector. T is the black vector. You're projecting onto the green vector, and by subtraction, you get the orthogonal complement, which is the red line. This is the vector. So context panel, norm, Euclidean, and then approximate to 10 digits. There's even an analytic solution to this problem. You simply minimize a distance from the point to the line. Okay, so this is the expression for the line. For every value of t, you have a point on the line. This is the line segment, the vector from P to that line. Get the norm and minimize the norm. So this is the vector. Compute its norm. Here I did a simplification and give it the name f. And then you're minimizing f. It's calculus 1. There it is, f. Differentiate with respect to t. You can do that through the context panel. Differentiate with respect to t. You get this expression. Maple's solve command assumes you meant to set it equal to 0. So here, let's do solve. Where did solve go? Solve. And you pick the simplest solve. You get t equals this. And you want to substitute that back into f. So there's a substitute into here. Substitute into. Now you type f over here. Say OK. You will get this. It's recognizable. We've seen that before. And if you float it, you see a decimal approximation that we've seen before. A fifth example. Here, let's leave it like this. Equation for the plane containing 3 points. So we'll go over here to where we can work on the problem. Here are 3 points. You want the equation of plane containing those 3 points. The syntax-free solution would go as follows. You would install the Student Multivariate Calculus package. Write the 3 points in a sequence. Points are lists, square brackets. Right click, go to the context panel. Select Student Multivariate Calculus, lines and planes. Pick plane. That will create this plane object. Go back here. Student Multivariate Calculus package, lines and planes, and you pick what you want out of this list. And we want representation, and Maple gives the equation of the plane. A command-based solution would start with the with command to load the package, create the plane object, apply the plane command to the list of, or the sequence of 3 points, and wrap that with a get representation command. You get the equation of the plane. The traditional vector solution can be implemented in Maple, but we're going to draw a picture first. This picture shows the plane. This down here is the origin, and the 3 blue vectors are position vectors to the points ABC. By pairwise subtraction, you form the green and red vectors. The cross product of the green and red vectors is this gold vector, which is the normal to the plane. Once you've got the normal, you've got at least 1 point, you've got the equation of the plane. So to do that, do those computations in Maple, you need the data to be entered. So A equals, B equals, C equals, and R equals. Generic position vector in space. Use the context panel, assign name, make those assignments. Pairwise subtraction, B minus A, C minus A, and you need a name for that. Again, assign name. Then you take the cross product of those 2 vectors. Cross product, I'll remind you, here I'll show you cross product. I've got a cross product symbol in my favorites palette. I got it from Common Symbols. You find it here. You right click, add to favorites, populate your favorites palette if you like. Again, assign name. That does the cross product and assigns it to n, and then the vector equation of a plane. R is a position vector to xyz. 1 point, I picked A. This vector has to be orthogonal to the normal, so the dot product has to be 0. That gives you the equation of the plane. There's an algebraic solution to this problem that I'd like to show you because it contains a bit of maple wizardry that you might not find otherwise. I'm going to define a scalar valued function of a vector argument. So the argument to this function f will be a vector. And what you use where you want the components of that vector to show up are indexed variables, not atomic variables, indexed variables, v1, v2, v3, because the name of the vector here I picked was v. So set this equal to 0, you got the equation of a plane. So to do that, you write the appropriate statement, and then in the context panel, use assign function. That creates the function f. A, B, and C have to satisfy f equals 0. So f at A equals 0, f at B equals 0, f at C equals 0. This is going to give you 3 equations in 4 unknowns, A, B, C, D. But there are really only 3 unknowns, because at least one of those has to be non-zero. Divide by that, and you've got 3 quantities that you need to find. So here are some equations. You can use the solve command. Solve for variables. A pop-up comes up, and you enter A, B, C for the variables. This then is the return. You get A, B, and C in terms of D. Use a substitute into, and you substitute it into f of r equals 0. R has already been defined. So you're going to get this as the return, and every term has a d in it. Easiest way to get rid of that d is to give it a nice value. So evaluate at a point, give d a value like negative 86, and you'll get the equation of the plane. It will differ from this equation only by a minus sign throughout. For a 6th example, we're going to get the equation of a plane that passes through or contains a given point and has a given vector for its normal. So let's go over here to a page where we can work on this problem. Point, normal. There is a task template that would be useful here, and I've shown where those task templates can be found. Tools, Task, Browse. In linear algebra visualizations, there is this plane plot interface to the plane plot command. So list the variables here. Normal, that's this vector, and the fixed point as a position vector. This slider controls the number of digits that will be used in this display down here. If this is clicked, it executes the code hiding behind here, code edit region. And what you get back from this command, this plane plot command, which is running in the background, the normal, which we already know, the equation of the plane, but it uses floats for the coefficients. Point on the plane that's nearest to the origin, and 2 basis vectors that span the plane. And then it draws this picture. Okay, so this is the origin. This vector points to that point on the plane nearest the origin. This red vector points to the fixed point that you use when you define the plane. These 2 blue vectors are the basis vectors. This is the normal. The solution using the lines and planes tools, first, syntax free. Well, we've seen similar calculations many times. Load the Student MultivariateCalculus package. This is the point. This is the normal vector. Make plane, you've seen that. Get the plane object representation, you've seen that. Equation of the plane. The command version of this solution would start with loading the package using the with command, applying the plane command to the sequence of point, normal vector, assign it to some name Q. Apply the get representation command to Q, and the reason for separating these two is so that I could apply the get plot command to the plane object whose name is Q. And then I picked a few options for the graph, and you can see piece of the plane, the fixed point, and the normal to the plane. Let's take a look at the traditional vector approach to this problem. Well, we've already loaded the student package. You need to define the fixed point as a position vector. This is the normal vector. This is the generic position vector, and they're all done with assigned name from the context panel. Then the vector equation of the plane is position vector r minus the fixed point. This vector has to lie in the plane, and to make it lie in the plane, you make it orthogonal to the normal. That's where the equal 0 comes in, and you get the equation of the plane. Example 7 asks for the equation of the plane that contains these two given points and is parallel to this direction vector, which means that that direction lies in the plane. So as you think about that, let's go over to this page. Think about that. These 2 points would determine a vector in the plane. This direction would give you a vector in the plane. If you took the cross product of those 2 vectors, you'd get a normal. You have enough information to determine the plane. Using the tools of multivariate calculus, lines and planes, a syntax-free solution, install the package. Now write a sequence. This is the direction vector, V. These are the 2 points, P and Q. Make plane, get a plane object, get representation for that plane object. There's the equation of the plane. A command-based version with these tools. Load the package, use with because you're working with commands. Use the plane command. There is that vector V. These are the 2 points P and Q. Make an assignment of the plane object so created. Apply the get representation command to that plane object. You get the equation of the plane. By separating these 2 commands, you can apply the get plot command to the plane object. You get a picture of the plane and it's normal. If the traditional vector solution is the approach, it really helps to have a figure. These 2 blue vectors are the position vectors P and Q. There's your origin here. By subtraction, you create this vector W. So W is this black vector. The red vector is V. It's that given direction. They look almost collinear, but they're not. And it's the cross product of the red and black vectors. Red and black cross product, usually the normal, which I've drawn in green. Once you've got the normal, you've got at least 1 point. you can write the equation of the plane. The implementation of what we just saw in that figure would be as follows. Of course, you need the package. You need to define P and Q as position vectors, the direction vector V, and the generic position vector R, and it's all done with the context panel assigned name. Subtraction, Q minus P gives you the vector W. Cross product, V cross W gives you the normal N. And the equation for the plane vector form is R, which is XYZ, less one of the points. This vector must lie in the plane. To make it lie in the plane, you make it orthogonal to the normal. That's what this equation is. And here you get the equation of the plane. There's an algebraic solution to this problem. It uses a device we have recently seen with a slight change. What we don't know in this problem is the normal vector on the plane. So let's have an unknown normal vector, ABC. So we define this n to be ABC, and you use a sign name. The function of the vector argument that we define that gives us the equation of the plane is n dot the components of the vector, which will essentially be an x, a y, and a z. So that's the name of the vector. These are indexed variables, not atomic. They're indexed variables. So we define that function using the context panel assigned function. There are three things we know about this plane. The vector v, that direction vector, has to be orthogonal to the normal. So n dot v equals 0. That's going to give us one equation. And then the plane must contain points p and q. So f of p equals 0, f of q equals 0. So three equations, four unknowns, and we know that one of those unknowns has to be non-zero. You divide by it. You're really looking for three things. So solve for three of the variables in terms of the fourth. Remind you what that would look like. Solve. You pick this one, solve for variables, and then there's a pop-up in which you put what you're solving for, ABC. When you get back this solution, you do a substitute into. So here is a substitute into, and you substitute into f of r equals 0. That's going to give you this equation. Every term has a d. Give d a nice value. Use value it at a point. If you give it negative 12, you'll get back this form for the equation of the plane. It's interesting to note that this is in lowest terms. Up here, it's not. It has every coefficient has a factor of 2. And when we did it way back here, the tools in the lines and planes section of multivariate calculus are also more efficient. They take out that multiple of 2. So for our last problem, I will jump down here to example 10. The distance from a point to the plane. So it's distance from a point to a plane. A syntax-free solution to this problem. Load the package. Write the equation of the plane. Create the plane object and give it the name Q. We've done that. Now, a sequence. The plane object, the point in question from which we're making the measurement. Evaluate and display in line so people can see what it is that it's looking at. Plane object, point. If you go here to the context panel here, Student Multivariate Calculus, lines and planes, you pick distance and you get 29 over root of 155. Suppose you wanted to do that from first principles and not have to rely on these tools of Maple. So you need a point on the plane. So there's the equation of the plane. If you if you use the context panel, Student Multivariate Calculus, lines and planes, point, Maple will find a point on that plane. It comes back as a list. It needs to be converted to a vector. So conversions, column vector, and then assign it to a name, so assign to a name A. Now by subtraction, we want a vector from that point to the point whose distance from the plane we want to know. So we subtract. This is the point P, and this is the point we just found A, and we subtract, and we get this point, and we give it a name V. We need a normal. So again, we go back to the plane, and we just query for the normal. There, you query for the normal. You give it the name N. Now, vector V, the normal N. Evaluate and display in line so Maple can see what it is it's looking at. We want to project this vector onto the normal, and then we're going to get the length of that. And so to do that, we make use of lines and planes, and there's a projection operator there. So we invoke the projection operator, and then it's this vector we want to get the norm of. And so here you get a norm operator right there. You pick norm, and you get the 29 over root 155. Command version of that calculation, bring in the package, use with. Plane command to create the plane object Q. Then apply the distance command, distance from Q to this point, and you get 29 over root 155. You want to use those tools to do solution from first principles. And here I've drawn the appropriate picture. There's the plane. Here's a normal. Normal is drawn from some point. You need a point, but you draw the normal. Up here is the point P that you want to, from which you want to measure the distance to the plane. By subtraction, you get this green vector. You project that green vector onto the normal. I've drawn that projection, that component here in black. It's the length of this vector that you really need to get the distance. So here is the point P. To get a point on the plane, you can use a get point command, and it'll come back as a list. You wrap it with the vector command, and it comes back as this vector V, the assignment operator. You can use the get normal command applied to the plane Q to get the normal, and then you can apply the projection command, projection of V onto N, and then you wrap it with the norm command, and you get to 29 over root 155. The traditional vector solution can be implemented as follows. I did a restart to clear memory, so I put back the package and define the normal vector. Just read off the components from the equation of the plane. You need to find a point on the plane. Here's the trick for finding the point on the plane. Pick an XY pair. I picked 0, 0. Substitute that back into the equation of the plane. I used evaluate at a point to do that. So x is 0, y is 0, 9z equals 11. So what you'll get, you solve that, or you can see that z is 11/9. Do a substitute into, and what do you substitute into? Substitute into the vector 0, 0, z. So you will get back the vector 0, 0, 11/9 and give that the name a. So there's your point on the plane. Then you need the vector v, which is from a to the point p. So by subtraction, you get the vector v. And then the scalar projection of v on n, v dot n over the length of n. And put absolute values here so that I get a positive distance, 29 over the square root of 155.